Hi everyone! Today, we'll explore the fascinating preparation principles of major food groups, dividing into the chemistry and techniques needed for different types of food. So here's our learning objectives. First, explain the role of gluten and yeast in making bread. Discuss the factors that causes chlorophyll degradation in vegetables. Demonstrate how heat and acids affect protein coagulation. And lastly, examine how enzymatic browning affects color, flavor, and food quality. First, let's talk about gluten's role, the anatomy of perfect yeast bread. So let's define what is gluten. Gluten is a protein found naturally in the endosperm of wheat. It gives strength, elasticity, and a characteristic chewy texture to yeast breads, pasta, and pizza dough. So how gluten form? First, water combines proteins forming gluten. Wheat and related grains like barley and rye contain two proteins, glutenin and gliadin. When mixed with water, these proteins combine to form gluten, which doesn't form without water. Second, mixing dough increases gluten development. The more you mix dough, the more gluten develops, making it elastic and stretchy. Gluten forms during kneading, but too much can make the dough hard to stretch. Third, excess gluten creates tough bread. The gluten is formed during kneading of the bread dough. However, if too much gluten is formed, then the bread dough does not stretch so easily. This will cause the bread to become tough and chewy. Fourth, resting dough reduces gluten elasticity. Relaxing or resting the dough reduces the elasticity of the dough, making it easier to roll out. Let's dive into the kneading process. So what is kneading? Kneading plays a vital role in building gluten networks. Kneading dough leads to the development of gluten and helps to uniformly distribute the gases that are produced by the yeast. The process of kneading. First, prepare a flat surface for kneading. It's easiest to knead dough on a flat surface around waist level. Just give your counter a quick clean, dry it well, and sprinkle a little flour so the dough won't stick. Second, combine the ingredients for dough. Use the right amount of flour and water. Then mix everything well with a wooden spoon. If flour is still sticking to the bowl, keep stirring. Your dough isn't ready to knead yet. Mix until everything comes together smoothly. Third, turn dough onto workspace. Dump it from the bowl onto flat surface you prepared. Fourth, gather and punch the dough. Work the dough with your hands, shaping into a ball, pressing it, and reshaping it. And lastly, observe tackiness and shape retention. The dough should feel slightly tacky and a bit elastic. If it's still lumpy or too sticky, keep kneading. Next is how yeast produces its texture. But first, let's define what is yeast. So yeast, it is a tiny living organism that makes bread rise by turning sugars into carbon dioxide and alcohol through fermentation. How yeast produce its final texture? First, by releasing carbon dioxide during fermentation. Yeast creates tiny air pockets that make the bread light and fluffy. These bubbles stretch the dough, giving it that smooth, soft, airy texture we love. The type of yeast used. The type of yeast you choose affects how quickly the dough rises and how much gas is produced. And lastly, temperature and hydration influence yeast. Warmer temperatures spread up yeast activity, while cooler temperature slows it down. Starch gelatinization is the process where starch and water are subjected to heat, causing the starch granules to swell. Next, is the process of starch gelatinization. First, water penetrates starch granules structure. When starch is heated in the presence of water, the water molecules penetrate the amorphous, disordered regions of the starch granules. Second, heating causes granules to swell. As heating continues typically between 60 degrees Celsius and 80 degrees Celsius, more water is absorbed. Third is the granule bursting. By providing continuous heating, the temperature increases, causing the granules to absorb more water and eventually rupture. Fourth is the mixture thickens, forming viscous paste. The release of amylose and the expansion of the granules cause the mixture to become more viscous. Fifth, cooling creates a firm gel network. As the mixture cools, the dispersed amylose and amylopectin molecules reassociate and form a gel-like network that traps water. Factors affecting starch gelatinization. First, temperature. Generally, starch gelatinizes on heating. Large starch granules gelatinize at a relatively lower temperature like in potato. Second, sugar. It competes with starch for the availability of water, thereby decreasing the onset of gelatinization. Last is the acids reduce starch gelatinization temperature. So the acid caused reduction in gelatinization temperature and enthalpy of gelatinization of both starches.
Now, let's talk about pigment retention in vegetables. Pigment retention refers to the ability of a substance to maintain its color and pigment properties over time, despite exposure to environmental factors like light, heat, air, or chemical. Pigment retention is crucial for maintaining the appearance and quality of products. Now, let's talk about chlorophyll. Chlorophyll is a green pigment found in plants, algae, and cyanobacteria that is essential for photosynthesis. In terms of pigment retention, chlorophyll can be affected by various factors like heat, light, and pH levels, which can cause it to break down or degrade, leading to changes in color and nutritional value. There are various factors why vegetables turn dull or olive. First is heat and acid causes magnesium ion to detach from chlorophyll. Also, enzymes contribute to breakdown, and longer cooking time increases pigment loss. Factors that affect chlorophyll color. First is heat. Heat speeds up chlorophyll breakdown. Prolonged cooking equals more phae-phytin formation. Next is acid. Acid accelerates magnesium ion removal. Naturally acidic ingredients like tomato, vinegar, lemon worsen color loss. The third factor is pH of water. Neutral water equals safer for pigment retention. Acidic water equals more color loss. Slightly alkaline water equals brighter green but risks musty texture. Techniques to prevent green color. First is blanching. Blanching is a quick cooking in boiling water. It inactivates enzymes that destroy chlorophyll. Prepares vegetable for freezing or further cooking. Second is minimal cooking time. Shorter exposure to heat reduces pigment damage. It is ideal for tender vegetables. Third is using neutral water. Avoid acidic additives during cooking and add acids only after cooking. It ensures chlorophyll stays stable during heating.
Now that we're done with pigment retention, let's proceed into achieving the perfect green, the principles of protein coagulation. When we say protein coagulation, it happens when the proteins in milk, cream, and eggs unfold and link together under heat or acid. I will discuss how tempering plays a key role in keeping everything smooth, controlled, and perfectly balanced. Let's start with the ingredients. Milk has casein and whey proteins, which act differently with heat and acid. Cream has fat, which makes it rich but still delicate. Egg whites firm up quickly and egg yolks thicken gently. Together, they form the base for custards and sauces. When we heat these proteins, they unfold and link together, which thickens liquids. Gentle heat gives smooth, creamy textures, but too much heat can make them curdle or get rubbery. That's why controlling temperature is very important. Acid works faster than heat. It pulls protein together quickly. For example, lemon or vinegar makes milk into curds. Too much acid can split cream, but acid also helps yogurt thicken. Heat works slowly, acid works fast, and both creates structure in dairy and eggs. In the kitchen, you can see this happening. Custard thickens gently and milk turns into ricotta with acid. Cream sauces can break if overheated.
Now let's talk about enzymatic browning. So what is enzymatic browning? It is a natural chemical reaction that happens in fruits and vegetables when they are cut or bruised, causing them to turn brown. This process is driven by enzyme and exposure to oxygen. Here are the steps of enzymatic browning. First is the cell damage. The process starts when the cell of the fruits or vegetable are damaged, such as when you cut, peel, or bruise it. This damage breaks open the cell walls, releasing enzymes and other compounds that were previously separated. The second step is the enzyme activation. One of the key enzymes involved is the polyphenol oxidase, or PPO. So what is PPO? PPO is normally kept separate from other compounds within the cell, but when the cell is damaged, it comes into contact with the oxygen. This starts the cascade of reaction leading in browning. The third step is oxidation. Once activated, PPO catalyzes the oxidation of phenolic compounds. This oxidation process converts the phenolic compounds into canones. And the last step is the polymerization. Canones are highly reactive and unstable compounds. They quickly undergo a process called polymerization, where they combine with each other and with amino acids or proteins. Each of these steps is crucial in the enzymatic process. While browning can be undesirable in some cases, like sliced apple, it can also be beneficial in others, like the development of color and the flavor in tea or coffee. To reduce or prevent enzymatic browning, we can use lemon juice, cold treatment, and blanching. First, let's talk about the lemon juice. So how it works? Lemon juice is acidic. It has a low pH. Due to the presence of citric acid, this acidity inhibits the activity of the enzyme. For example, cut one apple into two equal halves. Coat one half with lemon juice. Leave the other half as it is or coat it with plain water. Place both halves side by side and observe over time. The expected result: the half coated with lemon juice will remain significantly whiter and show less browning than the untreated half. The second method is the cold temperature. So how it works? Low temperature slows down the rate of biochemical reactions, including the enzymatic browning process. For example, cut an apple into two halves. Place one half in the refrigerator and other on the counter. And lastly, check both halves periodically or over time. The expected result: the apple half that has been exposed to the cold will brown more slowly than the other one left at room temperature. The last method is blanching. So how it works? Blanching involves a short immersion in boiling water. This high heat denatures and deactivates the enzyme responsible for browning, preventing the reaction from occurring. For example, peel and slice an apple. Take one set of slices and blanch them by boiling water for about a minute. Take a second set of slices and do not blanch them. And lastly, place both sets of slices on a plate and compare the color over time. The expected result. The blanched slices will retain their fresh color for a much longer period compared to the unblanched slices, which will brown quickly.
Overall, understanding the chemistry behind gluten, starch, pigments, proteins, and enzymatic browning helps us control the quality of food. By applying the right techniques, we can improve texture, color, and flavor in different dishes.